Alright, in this video we study the Hilbert Projection Theorem, which states the following. So we have a Hilbert space and its subset M, which should be also closed subspace, the meaning of which I will explain in this video. And then for each x in H, so every element in H in the Hilbert space, can be decomposed into two parts, x1 and x2. x1 is in M and x2 is in its orthogonal complement. That means x1 and x2, they are orthogonal to each other. So just like we could decompose any vector x in the real vector space into two parts, x1 and x2, which are orthogonal to each other, we can do the same thing in general Hilbert spaces. Okay, let's start. So first, let's define what a subspace means. So a subset of a Hilbert space, let's call the subset M, is a subspace. This means the following. For any element x and y in this subset, and any real numbers alpha and beta, the linear combination made by these vectors should be also in M. So if this holds, then the subset M is called a subspace of the Hilbert space H. And next, let's define what a closed set means. So again, the subset M of the Hilbert space H is called a closed set or closed subset. Subset if the following holds. So for any sequence in M, and if it converges and go to infinity xn, then this implies x, the limit x, belongs to M also. So if this holds, then we say the set is a closed subset. And if this subset happens to be also also a subspace of H, then we say it's a closed subspace. Next, let us explain one basic theorem that explains what can be a closed subspace of a Hilbert space. So suppose x1, x2, and so on up to xn are elements of the Hilbert space. Then consider the subset that is spanned by these vectors. So let's define M as M of x1 up to xn such that it's linear combinations of these vectors. So Cj are real numbers, j from 1 to n. So this is the set of all the vectors that can be expressed as a linear combinations of these vectors. So in this sense, we say this subset is spanned by these n vectors. So if we define M in this way, then this M is a closed subspace. So let's prove this. So in order to prove that this M is a closed subspace, we need to prove that it is a subspace and it is also a closed set, right? But proving it is a subspace is actually trivial, but just in case, I'll prove it. So if x and y are in M, so that means x and y can be represented as a linear combination of these vectors. So then x can be expressed as, let's say, j from 1 to n, aj, x, j. And y similarly can be expressed as a linear combination of these n vectors. So let's say bj and xj. So if we add, so alpha and beta are any real numbers. So for these, we have sum of j from 1 to n, and alpha times aj plus beta times bj and xj. So this is of course a real number, so this belongs to M. So it is a subspace. And next we need to show that it is a closed subset, but first of all, if these n vectors are not linearly independent, then we can remove some of the vectors until all of the vectors are linearly independent. So we just assume that all of them are linearly independent without losing generality. So assume x1, x2, xn are linearly independent. Then apply the Gram-Schmidt process. Gram-Schmidt. To find the set of orthonormal vectors. So to find E1, E2, En such that they are orthogonal. Ei, Ej, this is Kronecker's delta. And the subspace M can be expressed as a linear combination of these orthonormal vectors. So J, E, J. Okay. Now, suppose we have a sequence of vectors. So let's say AK, which is a subset of M, and also assume it converges. Okay, limit. Then we want to show that this limit also belongs to this subspace M. So how do we do that? And since this sequence belongs to M, that means each term here, AK, can be represented as a linear combination of this form. Right? So let's write that as this, j from 1 to n, and a, j, k here, and ej. Okay. So for each term ak, we have these coefficients. We next show that for each j, this coefficient makes a Cauchy sequence. Okay, so for that, let's calculate the difference between, let's say, aik and ail. So we want to show that this converges to 0. Okay, and this is less than or equal to sum j from 1 to n, the difference between ajk minus ajl squared and square root. But this is the norm of the difference between ak and al, because we are representing ak and al using this orthonormal basis. And of course, we are assuming that this sequence of vectors is a converging sequence. So this is, of course, converges to 0, but just in case, let's show that explicitly. So using the triangular inequality, this is less than or equal to ak minus a, and al minus a. Yeah, a is this one, so the limit of this sequence. Okay, So this converges to 0, and this converges to 0. So everything converges to 0 as k and L go to infinity. So that means, so therefore, for each I, ai, k, k from 1 to infinity is a Cauchy sequence. Cauchy sequence. And of course, this is a sequence of real numbers, and the set of real numbers is complete. Therefore, this sequence converges. Okay, so since R is complete, limit k going to infinity ai k exists. Of course, in the set of real numbers. So let that limit be ai. And consider the vector j from 1 to n and aj. So using this ai, let's define a vector as this. Then we show that this actually is equal to the limit of the vector sequence. So this should be equal to this vector A. Let's show that. So let's take the difference between this vector and A. So this is greater than 0, of course. And using the triangle inequality, for any k, we have this. A j e j minus a k. So this k is arbitrary. Plus a k minus a. Okay. And this ak can be expressed as this, right? So this is so using that representation, we have a j minus a j k here, and e j. But this one, this norm is equal to the sum of aj minus ajk squared and square root. But we have seen that this sequence, so k varies from 1 to 3 and so on, converges to this aj. So this means each of these terms converges to 0. And this one, of course, converges to 0. So this everything converges to 0 as k goes to infinity. So that means this is converges to this. So therefore, A is equal to the sum aj ej. And of course, this does belong to M because it's spanned by these vectors. Therefore, M is a closed set. And we are done. In the next theorem, we introduce the orthogonal complement of a subset. So let S be a subset of the Hilbert space H. Subset. It doesn't have to be a subspace, it's just a subset. Then let us define S complement as this. So it's made of vectors in H such that for all vectors in S, it is orthogonal to it. So S complement is made of all the vectors in H that are orthogonal to every vector in S. Then S complement is a closed subspace of H. So to prove this, again, we need to prove that it is a subspace and it is also a closed set. So proving the subspace part is quite easy, actually. So let's say if we have Z and Y and Z in S complement, then for any alpha, beta in real numbers, the linear combination of Y and Z, let's say Y alpha Y plus beta Z and X, and let's say X is any element in S. Okay, so this is equal to, so by the properties of the inner product, this is equal to alpha Y X plus beta Z X. But since Y and Z are already in S complement, so this is 0, this is 0, so this is 0. Therefore, alpha Y plus beta Z is in S complement. So it is a subspace. And to show that it is a closed set, suppose we have a sequence Yn, which is a subset of S complement, and it converges. Okay, and we need to show that this Y belongs to S complement. Well, we have seen that the inner product is continuous. So Yn times X, of course X is an element of S. So if we take the limit of this inner product, this should converge to, by the continuity of the inner product, this converges to Y times X. But Yn times X is always 0 for any n natural number. Therefore, the inner product between Y and X, because inner product is continuous, this should be also 0. Therefore, the limit Y belongs to S complement. Therefore, it is S complement is a closed set. And we are done. Next, let M be a subspace of H. So not just subset, but it's a subspace. Then the intersection between M and M complement consists of only 0 element. Of course, this 0 element means the 0 vector in the Hilbert space. So let's show this. To show this, suppose X belongs to this intersection, M cap M complement. Then X belongs to M and X belongs to M complement. So that means the inner product between X and X should be equal to 0. So this implies X should be the 0 vector, and we are done. Now let's turn to the main theorem of this video, that is the Hilbert Projection Theorem. Actually, what we prove here is a bit restricted version of the original theorem, because the generality of the original version is not necessary for our purpose here. Okay, let M be a closed subspace of H. It's a closed subspace. And for any point in H, any vector in H, we define the distance between X and M, so it's a closed subspace, to be the infimum of the distance between X and Z, where Z moves in M. Okay, then there exists a unique, let's say unique, Y in M such that this distance is equal to the distance between X and Y. Here, this 1 indicates uniqueness, okay? What this theorem means is the following. If we have any point X in the Hilbert space, and if we have a subspace, a closed subspace M, then we calculate the distance between any point in M and the point X. So we calculate the distance, 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 and so on. But there will be a single point, unique point, where the distance is the minimum, and that will be the Y, this Y. And in a later theorem, we will see that the vector x minus y, so that will be something like this vector, okay? So this vector will be orthogonal to M. Anyway, let's prove it. First, let D be distance between X and M for convenience. Now, note that for each natural number n, there exists an element yn in M such that the distance between x and yn is greater than or equal to d squared, square distance, and that is also less than or equal to d squared plus 1 over n squared. So we can construct a sequence of yn in M in this way. And let's apply the parallelogram law to let's see, x minus ym and x minus yn. So this is 0 is less than or equal to, so this minus this, ym minus yn. This is greater than, not greater, no, it's equal to, so 2 times this, x minus ym plus 2 times x minus yn, and minus this plus this, so that's 2x minus ym minus yn. Now, using this inequality, this is bounded by 2 times d squared plus 1 over m squared and 2 times d squared plus 1 over n squared. And let's factorize 2 out and minus, wait a minute, so this should be squared. And factorizing 2 out, so 4 will be out, and x minus ym plus yn over 2 squared. And let's rearrange this a little bit. So we have 2 over m squared plus 2 over n squared. So, and we have 2d squared from here. So this is minus 4 and x ym plus yn over 2 squared minus d squared. Okay, now since M is a subspace, this point, the average of ym and yn, this is also an element of M. Okay, but d is the infimum of the distance between x and a point in M, so this quantity is greater than or equal to d. So this part should be positive. So we have minus positive number. So if we discard this one, this quantity should be less than or equal to 2 over m squared plus 2 over n squared. And this converges to 0 as m and n go to infinity. So that means the sequence yn is a Cauchy sequence. But H is complete because it's a Hilbert space. And M is closed. Therefore, the limit, so because of the completeness, it has a limit yn, n going to infinity, and the limit belongs to M. So we have proved the existence of an element y in M that minimizes the distance between M and X. Next, we need to show the uniqueness. So to show the uniqueness, suppose there exists another y prime such that the distance between y prime and x is equal to d. So using this, 2d squared is equal to x minus y, the distance between x and y squared, plus the distance between x and y prime squared. And again, using the parallelogram law, we have, so if we add these two, we have 2x minus y prime squared, and this minus this, y minus y prime squared. Okay, let's rearrange a little bit. Let's factorize 2 out, and we got 4. We got divide by 2. That's 2 x minus y plus y prime over 2 squared plus 1 over 2 y minus y prime squared. And again, y plus y prime over 2. This element belongs to M. So the distance between x and this point is greater than or equal to d squared. So less than or equal to 2d squared plus 1 over 2 y minus y prime squared. But here we have 2d squared here, 2d squared here, and this quantity, y minus y prime squared, this is non-negative. So for this to be, so therefore we have 0 greater than or equal to 1 over 2 y minus y prime squared. But this is, of course, greater than or equal to 0. So we have this. We have to conclude that y minus y prime, so this distance must be equal to 0. So this indicates y must be equal to y prime. So the point where the distance is minimized is unique, and we are done. An important consequence of the Hilbert projection theorem is orthogonal decomposition. Okay, so let M be a closed subspace of H, just like the previous theorem. then for any element x of H, there exists a unique pair x1 and x2 where x belongs to M and x2 belongs to the orthogonal complement of M, such that x is equal to x1 plus x2. So let's prove this. And first of all, by the Hilbert Projection Theorem, there exists a unique x1 in M such that the distance between x and M is equal to the distance between x and x1. Okay, so we will see this x1 will be this x1. And let x2 be x minus x1. So this x2 will be this x2. So what we need to show is that this x2 belongs to M complement. Okay, this is to be shown. And to show this, we need to show that for any element y in M, the inner product between y and x2 is equal to 0. So we need to show this. And we show this by contradiction. So suppose there exists some y in M such that the inner product between y and x2 is some constant c which is non-zero. Okay, so by redefining y as y over c, we may assume that this inner product is 1 without losing generality. And we note that the norm of x2 is equal to x, by definition of x2, it's x minus x1, which is equal to d, which is the distance between x and the subspace M, the minimum distance. Now, for any t in real number, we have d squared less than or equal to the distance between x minus x1 plus some real number t times y squared, because d is the infimum of this distance. Okay, now this is equal to x2. So x minus x1 is x2 minus ty distance. And if we expand this, we have x2 squared minus t x2 y and plus t squared y squared. And we assume that this is 1. And this is d squared. So d squared minus t plus t squared and y squared. So let's complete the square here. And we have, let's see, so yt and minus 1 over y. This y is non-zero, assumed to be non-zero, so it's okay to divide by that. And squared and plus d squared and minus 1 over y squared. And if t is equal to 1 over y squared, y norm squared, so if we substitute t here, then this part becomes 0. So we have d squared is less than or equal to d squared minus 1 over y norm squared, which is a contradiction. This is a contradiction. Because that will be negative number is greater than 0, which is a contradiction, of course. Anyway, so therefore, our assumption that this inner product is non-zero was incorrect. So therefore, y for any y, the inner product between y and x2 is equal to 0. And therefore, x2 belongs to the orthogonal complement of M. Now we have this decomposition, x equals to x1 plus x2. And next, we need to show the uniqueness of this decomposition. So suppose we have another decomposition, x1 prime plus x2 prime, where x1 prime belongs to M and x2 prime belongs to M complement. Then we have this equals to this, right? So x1 plus x2 equals to x1 prime plus x2 prime. So by rearranging this, we have x1 minus x1 prime equals to x2 prime minus x2. Now, this is a subspace, and the complement is also a subspace. So therefore, x1 belongs to M, x1 prime belongs to M. So therefore, this belongs to M, and this one, x2 belongs to M complement, x2 prime belongs to M complement. So this belongs to M complement. So these vectors belong to both M and M complement. That means x1, they belong to the intersection between M and M complement. Therefore, as we have seen before, the only element that belongs to this intersection is the 0 vector. So x1 minus x1 prime is equal to 0 vector, which is also equal to x2 prime minus x2. Therefore, x1 is equal to x1 prime and x2 is equal to x2 prime. Therefore, the decomposition is unique, and we are done. So given a closed subspace of a Hilbert space H, we can decompose the entire Hilbert space into two parts. One is M, and the other is M complement. And we write like this. So it's a direct sum between M and M complement. So if we write x equals to x1 plus x2, and where x1 belongs to M and x2 belongs to M complement, we write x1 as the projection of x onto M, and x2 is a projection of x onto M complement. So this is a projection operator. And as we have seen in the proof of the previous theorem, this x1 was determined as the distance from the distance between x and M. So if we have x here somewhere in the Hilbert space, then if we have this subspace M, then x1 is the point in M that is closest to x. And x2 is defined as this vector. Okay. x2 is x minus x1. And we have seen that this is orthogonal to M. So this is why we call this an orthogonal decomposition of X. And I say this is a projection operator, and this does indeed have the properties of a projection operator, as we see next. So first of all, this Pm is a linear operator. Let's show this. From now on, for brevity, we just write P for Pm and Q for Pm complement. So first we have this decomposition, x equals to Px plus Qx, and y equals to Py plus Qy. So if we add both sides, we have x plus y and Px plus Py and Qx plus Qy. Okay, on the other hand, this is also, so we decompose x plus y at the same time. So we have P time of x plus y and Q of x plus y. Okay, but the decomposition is unique. And remember, Px and Py, they all both belong to M, and Qx and Qy, they belong to M complement. Since M and M complement, they are both subspaces, this sum is also in that same subspace, so M and M complement respectively. So by the uniqueness of decomposition, this is equal to this, and this is equal to this. So therefore, P applied to x plus y is equal to P applied to x plus P applied to y. And similarly, this one is this. Okay, so for the summation, it's almost linear. And one more thing we need to show is that so if we have x Px plus Qx, if we multiply both sides by alpha, so alpha is any real number, we have alpha, alpha, alpha. Okay, on the other hand, we should have the decomposition of alpha x. So that should be P of alpha x and Q of alpha x. And again, since M and M complement, they are subspaces, this thing is in M and this thing is in M complement. And by the uniqueness, again, this should be equal to this, and this should be equal to this. So we have P of alpha x is equal to alpha of Px. And Q of alpha x is equal to alpha of Qx. So from these two, we have, we conclude that P and also Q is a linear operator. And next, we show that the inner product between Px and y is the same as, is equal to, the inner product between x and Py. Okay, let's show this. So this is equal to, first let's decompose y into two parts, Py and Qy. So by the properties of the inner product, we can split this Px, Py plus px plus qy. But this and this are orthogonal, so this inner product is equal to 0. So we have only px and py. Now, px is equal to x minus qx. And again, we split this inner product, and x times py minus qx times py. But this and this, qx and py, they are orthogonal to each other, so this is 0. So we have x times py. So we can move the place of p from the first place to the second place, just like the projection operator we have seen before. And the final property is this. If we apply the operator p twice, then its effect is the same as applying it only once. For this property, we call it p is idempotent. Okay, let's show this. First of all, let's decompose px first. So px plus qpx. And of course, px is equal to px plus 0, right? It's trivial. Now, by the uniqueness of decomposition, we should have, okay, so this part is in M, okay? This part is in M. This part is in M complement. So, and this part should be in M complement. So therefore, qpx is 0, and px should be equal to px, and we are done. Okay, that's it for this video. See you next time. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.